Okay, so now we look at the conditions for equilibrium. The first condition of equilibrium stated that if you sum all the forces in the x direction and they come out to zero, sum all the forces in the y direction and they come out to zero, then you are in the first condition of equilibrium. An object has no external forces acting on it. The object either remains at rest or it moves with a constant velocity if it happens to be in motion. The second condition of equilibrium asserts that if an object is in rotational equilibrium, the net torque acting on it about the axis, any axis, must be zero. So we use our first conditions of equilibrium in forces, F sub x, F sub y, and the second condition of equilibrium for torque. A body in static equilibrium must satisfy the two conditions then. The resultant external force must be zero, and the resultant external torque must be zero. So if the object is in equilibrium, it does not matter where you put the axis of rotation for calculating the net torque. The location of the axis is completely arbitrary. So we're going to see where this comes into play and becomes important when we start looking at centers of gravity. And voila, here it is. So you can see we've got some irregular blob here, irregular shape, random shape. The center of gravity of a homogeneous symmetric body must lie on the axis of symmetry. So what we do here is we're going to take all of our mass and gravities and we're going to sum them together for each of the points that we see here. Mass 1, gravity, mass 2, gravity, mass 3, gravity, and then we've got a center of gravity here that relates to the weight of the object in a balanced position, if you can think of it that way. If you've ever tried to take an irregular shape and find out where it balances just right, well, that's what the mg is going to be. So we sum all of those and we multiply it times the distance for the center of gravity, and we can simplify this then by saying that the center of gravity, x sub cg, then is the sum of all of the mass times the distances in the numerator and all of the masses in the denominator. And again, we simplify it using our summation symbol, sigma, mass I, distance I, divided by mass I. Okay, so in every case, it'll be a summation of all those points. Similarly, the y-coordinate of the center of gravity of the system can be found the same way. So if you look at this, it says y center of gravity, the same terms, the same simplification. So we're using components x and components y of the center of gravity to try to determine, in, for example, this irregular shape here, where the center of gravity would lie, x sub cg, y sub cg, given we have all of these individual measured masses and gravity shown for the object. So let's take a look at an example. We've got three balls here. Each of them weigh a different amount, have a different mass, and they are placed at 1/2 and 1 meter from the center axis here. So three particles are located in a coordinate system. Find the center of gravity. So the first thing to do is gather up each of your given amounts. So we know that m, 1, 2, and 3 are given by the masses of the balls or the particles, and then the distances are shown for x1 minus 1/2 meter, x2 lies right on the x-axis 0, and x3 1 meter. So we find the center of gravity then by summing all of the x components in this relationship. So if we sum all of the m times x components, we have 5 kilograms times minus 1/2 meter, 2 kilograms, 0 meters, so we know that term is going to disappear, and 4 kilograms times 1 meter. And what we end up with then is a summation that says minus 2.5 from 4 gives me 1.5 kilogram times meters. Okay, so because that's the product of each of these. So the x sub g then would equal all of those terms for mixi in the numerator, and we divide by the sum of the masses. So 5 plus 2 plus 4 gives me 11 kilograms. We end up with a distance of 0.136 meters as the center of gravity. So it's going to be, just slightly off of the y-axis where the center of gravity occurs. Let's look at an example here, walking a horizontal beam. So we've got a horizontal beam here that's got some components of force or tension on it. At a given angle, we've got an amount, looks like the center of gravity there, and then 600 newtons. So the question says a uniform horizontal beam of 300 newtons, so there you can see that in the free body diagram, 5 meters long. Okay, we know that that's the length of the beam, and it's attached to a wall by a pin connection that allows the beam to rotate. Its far end is supported by a cable that makes an angle of 53 degrees, so there's our tension, there's our rotator there. 53 degrees from the horizontal. Okay, so from here up is 53 degrees. If a 600 Newton person stands 1.5 meters from the wall, so there's our designation, 600 meters, 1.5 meters from the wall, find the tension in the cable and the force exerted on the beam by the wall. So we're looking to see what force the beam has forces exerted by the wall. So we gather our knowns. So the mg of the beam, 300 newtons. The length, 5 meters. Mg of the person, 600 newtons. And the distance the person walks out on the beam, 1.5 meters. So now what we're going to do is, let's skip down to the free body diagram here on the bottom where we've got everything marked off. So we've got the tension times the sine of 53, the tension times the cosine of 53, Ry and Rx, we don't know, that's what we're solving for. But we know all of the distances for each of these force measurements, 300 newtons and 600 newtons. So we're going to start with the first condition of equilibrium. Sometimes sometimes you can start with that and it works out. Sometimes you can start with the second condition. But we're going to start with the first condition of equilibrium. So if we sum all of the forces in the x direction, we have the unknown r sub x minus t cosine 53, and we set it equal to 0 because it's in equilibrium. Summing all of the y forces, r sub y plus t sine 53 degrees minus 600 minus 300. Okay, so all of these are pointing up, all of these are pointing down, hence the minus minus. So now we've gotten as far as we can. Let's go ahead and write the relationship for the second condition of equilibrium. So if we sum all of the torques in this relationship, as we move along here, we have t sine 53 at 5 meters. So that's just telling us that all the way out to the end here of 5 meters, we have a tension component of t sine 53. Let's move back one, the 300 newtons. So the 300 newtons, we have minus 300 newtons times its distance, which is halfway, 2.5 meters. Let's move to where the person is standing, 600 newtons. We have 600 newtons. They said he was 1.5 meters off of the end, and there are no other terms then to capture because out here at the end there is no torque. Okay, so we set all that equal to 0. So now let's rewrite the expression then. T sine 53 times 5 meters equal to 300 newtons times 2.5 meters plus 600 newtons times 1.5 meters. We do this so that we can get now the term for the tension T by itself. So we're going to pull all of the other terms to the other side of the equation. So all of this on the right is the numerator. The 53, the sine 53 times 5 meters becomes the denominator. When we run those through our calculator, we get 1650 Newton meters divided by 3.99 meters. And that ends up giving us the tension in the cable at the far end of the beam 413 newtons. So we've found what the tension is out here on the far end. Okay, so the next thing we're going to do then is we're going to solve for the Ry and Rx term. Remember, that is the rotation point on the near end of the beam. So R sub x is equal to T cosine 53 degrees. Okay, so R sub x in the positive direction, T cosine 53 in the negative direction. So we end up with, we just solved for T, 413 newtons times the cosine of 53 degrees gives us R sub x of 249 newtons. So that's the x component. Now I can solve for R sub y. R sub y is 900 newtons. That's the sum of the 600 and the 300 newtons downward, minus T sine 53 degrees. So that's on that end, on the far end. And so when I solve, I substitute again 413 for T. So 413 sine 53 minus 500 newtons gives me R sub y of 570 newtons. Okay, so now we're going to leave our relationships for torque and equilibrium, solving for the second condition of equilibrium, and we're going to look at torque and angular acceleration.